Right, a light dependent resistor, an LDR, has a low resistance in light, in high light intensity, and a high resistance in the dark. Right, the question wants us to sketch the graph of resistance versus light intensity. So this is an exponential decay curve. Right, so we have resistance on the y-axis, so we write resistance here. Of course, this is in ohms. Then on the horizontal axis we have light intensity. Right, the units for light intensity is candela, that is CT. So this will always be an exponential decay. Right, so as light intensity increases, the resistance will drop, and vice versa. So this is how the graph will always look like for light intensity versus resistance of an LDR. Right, Fig 5.1 shows part of an electric circuit used to turn on a light when it's dark. Okay, complete the circuit in Fig 5.1 with the symbol for an LDR. So in LDR, you just draw with the ruler, of course. Right, it's a resistor with some arrows that show that its resistance depends on light. That's the LDR. Some people, they put some circles there around. It's still okay to put a circle around that resistor, but what is important is to show that there's some light coming onto that resistor. Okay, explain why the lamp is off in the light and why the lamp is on in the dark. Use ideas about the potential difference, PD, in your answer. Right, we call this circuit a potential divider circuit. Okay, potential divider circuit. Why do I say so? Right, we see here we have some source like of power there, so we can call this V in. Right, so V in is actually shared between this portion, right, and this one. Okay, so at across the LDR and the lamp there, we can have our V out, the voltage out there. We know we'll always have the same voltage because they're in parallel. Okay, so what happens is that, let's take for instance, if I have 12 volts here, and it happens that I have 9 volts across the fixed resistor, it means I will have 3 volts across the lamp or the bulb and the LDR. If I change there and have 5 volts probably somewhere on that one, it means here I'll have 7 volts. So voltage will always be shared between those two portions depending on how much resistance is there across that region. So the region with high resistance will always have more voltage. All right, so an LDR, since its resistance varies with light, it means that when light intensity is high, we have low resistance, and in that case it means that we'll have low voltage across that region, and more voltage will be pushed towards the fixed resistor, and vice versa. So in our case, the question wants us to explain why the lamp is off, why the lamp is off in the light. So we're saying in the light, right, in the light, the resistance of the LDR, right, when we have a light, it means we have high intensity. So once we have high intensity there, it means we will have low resistance. So I'm saying in the light, the resistance of the LDR is low. Okay, so according to the principles of a potential divider circuit, once we have low voltage, low resistance across this region, it means you are going to have low voltage. We're going to have low voltage in that region. So that means the low voltage probably is not good enough to switch on the bulb. So in the light, the resistance of an LDR is low, hence we have low potential difference across the lamp. That's why it stays off. Then in the dark, the resistance of an LDR increases. It's high this time around. So once we have high resistance here, the high resistance imply that the potential difference across the region is going to increase. And once it increases, it means it's now good enough to power the lamp. Right, so the resistance of an LDR increases, hence the lamp will switch on. Right, so this is what is very key. We have a potential. Of course, we can use some formulas. There are formulas that are used to calculate V out there. Normally, if this is resistor 1 and this is resistor 2, if you want to find V out there across the LDR, we say V out is equal to R2 divided by R2 plus R1. So it's like we are sharing, it's a ratio, right? We're calculating a ratio. Is that portion, right, divided by the total resistance times the V in. Okay, times the V. That's how we calculate it. If you want the V out across the fixed resistor, it means you'll be having R1 over R1 plus R2 times V in. So yeah, you can use these formulas in case there are some calculations that are involved in this particular question. But in our case, we just are supposed to explain things. So this is how you can write down your answers. I hope we learned something here. See you next time in our next session.